In this lecture, we are going to give an example of what category theory is about. So we've been looking at a few concepts and results in category theory. But maybe what we've done so far hasn't yet shown us the essence of the subject itself. These concepts and these results arise from a certain way of looking at mathematics. And that way of looking at mathematics is a bit different maybe from what now is regarded as the traditional way of looking at mathematics, which is to solve problems. Sure, mathematics and solving problems are very close to each other. We know how many problems in real life can be solved using mathematics. But an important fact is that very often mathematics develops by contemplating on concepts that arise when you try to describe the world around you or try to understand a certain phenomenon without necessarily at that point in time being focused on solving any specific problem. And in a sense, that's what mathematics was always about when it became a subject of its own. Even the concept of a number arises by a certain process of abstraction, which, yes, one can say that it was a necessity in order to solve some problems. But there are steps in this process which are not necessarily guaranteed by that necessity, and a mathematician is someone who takes these steps. And that's why after so many thousand years of development of mathematics, we have a lot of pieces of mathematics today which are quite far from direct application to real life, but maybe they're far today, but that changes after a couple of hundred years, as the history has shown that process definitely takes place, where concepts that have been developed 200 years ago get applied today. So we're going to take that approach. The category theory is very much about that approach, and you want to kind of you got this realm of a very complicated realm and a very rich and vast realm of mathematics, and so you take that as your universe in a way, and you try to understand some phenomenon in there. So the example on which we will demonstrate this process will be the category of sets. And what we're going to try to understand is exponentiation of sets. So we're going to call this lecture exponentiation. Well, we all know what exponentiation of numbers is. For example, 2 to the power 3 is 8, right? How do we get 8? Well, we can say that we get 8 by multiplying 2 with itself 3 times. This looks rather dry, though, in the sense that you want to know, I mean, why would you want to multiply 2 or 3 times? Is there any situation in life where we are urged to do something like that? After a bit of thought, one starts to see that this is a very natural thing to do. For example, when you want to consider a set of 3 elements, a set of 2 elements, and then you want to count how many functions you've got from a set of 3 elements to a set of 2 elements. You see, for each element of x, you have 2 choices where they can map. And because the choices are independent, the 2 multiplies with itself 3 times. But you might say that, okay, how is this related to real life? And then I will tell you that, well, it very much is, because this set of 3 elements could have been maybe a set of 3 books. So we've got 1 book there, a 2nd book there, and a 3rd book. And now you want to arrange your books on 2 shelves. And the question is, in how many ways you can do that? So you could put 1 book there, the other book there, and the 3rd book also there. That's, of course, the same as describing a function from 3-element set to a 2-element set. So this brings us to a realization that in fact, a number theoretic exponentiation in its root has something set theoretic. So what is set theoretic exponentiation? Y to the power x is the set of all functions from the set x to the set y. We no longer want to count them, we just want to consider the set. Okay. Well, this is something that's happening in the category of sets, right? So we've got the category of sets. Let's draw this vast area, the universe of sets seen as a category. And now I know that in this category something special is going on. For any 2 objects in the category x and y, I could consider morphisms between them. The category allows to do that, right? And in the category of sets, these morphisms are precisely functions. But then there is something else I can do, which is quite peculiar, that I could consider the set of these functions as a separate object in the category. And so in the spirit of what I said originally, we want to understand a phenomenon. And for us now, for category theorists, we no longer see mathematics as something ad hoc. We see every type of phenomenon occurring in mathematics as some specific phenomenon of a specific category, or maybe something a bit richer than a category. And now I want to ask the question, okay, what about other categories? Can I have similar phenomenon in other categories? But in order for me to investigate whether I can have similar phenomenon in other categories, I first want to describe the phenomenon in the language of category theory, so that I can transport it to other categories, which are different from the category of sets. Okay, so we will actually do that. So we will in the end, towards the end of the lecture, we will see how this phenomenon of exponentiation does arise in other categories as well. And we will have at least one very surprising example, which looks nothing like sets, where exponentiation obtains completely different meaning, not less significant, maybe even more significant in some sense, but completely different from exponentiation of numbers. So to be able to abstract the notion of exponent, we want to express the definition of y to the power x in the language that only makes use of objects and morphisms and their composition. Here, we haven't done that yet. We have made use of the language of elements because we've described what elements this thing has, right? But we did talk about generalized elements already. And so perhaps we could try to describe generalized elements of this object. Let's see. So first, the standard generalized element would be the one that that has as its domain the single object set. And of course, the single object set is very much categorically describable. It is the terminal object in a category. What is a terminal object? It's an object to which there is exactly one morphism from any other object. And to be honest, I can't recall if we have already dealt with the notion of a terminal object or not. Maybe you can recall. If you do, please tell me. If we haven't dealt with it, then I'm going to recall it here. One is an object in set such that there is a unique morphism to one from each given, from each object C. And I think it's quite obvious why we have a unique function from any other set to the singleton, right? Okay, so we pick this terminal object, the singleton, and then the generalized elements whose domain is the singleton, they are simply elements of this set, right? Because to specify an element of this, to specify a function from a singleton to this set, we just need to say what's going to happen with the unique element of the singleton, where it's going to be mapped to, right? And so specifying where this is going to be mapped to amounts to specifying an element of that thing. Now let's give an attempt of describing, okay, but I mean, so we could now say that there is a bijection between the elements of y to the power x parameterized by 1. So in other words, between the Hom set 1 y to the power x. So remember this notation here. Hom represents the set of functions from 1 to y to the power x. And we have a bijection between this set and the set Hom xy. In fact, maybe we could even use already this thing as a sort of definition of exponential. We could say that exponential y to the power x could be defined as an object such that there is such a bijection. The question is whether this definition will be good enough or not. Let's test this idea. So if we did define exponential objects in terms of existence of a bijection like this, would we recover exactly the exponentials in the category of sets? So would this be the only thing satisfying such a bijection? So we get now going to solve an equation that involves Hom sets. At school, we solve equations that involve variables, that involve numbers, and now we want to solve an equation that involves objects in a category. So specifically in the category of sets. Can we think of a situation where we have a bijection like this? But this thing is not the same as y to the power x. Well, I mean, if we have a bijection like this, certainly whatever this question mark is, certainly that question mark will be bijective to that Hom set, because because there's definitely a bijection between functions from a singleton to a set and the set itself, simply mapping every function to its value, since there is only one value that will give us a bijection. And this one we already know that it's bijective to, basically by definition, it's actually equal to y to the power x. And so we do get that the question mark will indeed be the exponent. Okay, so that kind of is good news, because it seems like we now have a definition for exponentiation. It turns out that exponential object in the category of sets has even stronger property than this one, where we replace 1 with any other object, but then we have to suitably adjust this thing over here. Why do we want a stronger property? Well, because when you generalize something, you want to have a general notion that you will be able to use in proving theorems. So maybe generalizing some theorems from the category of sets to other categories where we would apply this notion. And so you want your concept to be as powerful as possible. So if there is a natural way of strengthening this requirement to get maybe a better exponential object in a category, then why not make use of that? And the stronger property than this is the following one. So we could replace 1 with any set, let me call this set Z. And then on this side, we will have Z multiplied by X instead of X. Before I explain this bijection, let us look back here, and let me just add one more comment about why I wasn't happy with this as a definition. So I already said I want a strong property. The other thing is that the terminal object does not always classify elements of the object you're looking at. It's a very specific feature of the category of sets. And a good example there is the category of vector spaces, where the terminal object is the zero-dimensional vector space, and then you always will have only one morphism going out of that vector space to any other vector space, the linear map that maps the unique element here to the zero vector there. And so then you'll be forcing I mean, whatever you put here, this Hom set will always be one element set, and then you'll be forcing that this object is such that Hom xy is in one element set, so that'll be a very uninteresting situation where you only have one linear map from x to y. So basically, you will only be able to form exponents when either y is the zero-dimensional space, so that you have exactly one linear map, or the other way around, where x is the zero-dimensional space. So although 1 is an important object in the category of sets because it classifies elements, in other categories, the terminal object no longer classifies elements. And that is actually why we want to switch from elements to generalized elements, where we allow any object in the place of 1 to classify things. And that's another motivation, maybe more grounded, to considering an object Z in the place of 1. Okay, so let's come back here and let's get convinced that we indeed have such a bijection. So given a function f from z to y to the power x, I want to create a function from z cross x to y. So I have to decide where I'm going to map the pair zx. Any ideas where I could map that pair based on a function f from z to y to the power x? So what does f do? F maps an element of z to a function from x to y, right? Each f of z is a function from x to y. So z gets mapped to such a function. Can we use the function f to define a function from z cross x to y? To do that, we'll have to decide where to map the pair zx.
You could map each pair to the value f of z of x once you've yeah.
Fantastic. Yes, we can do that. That's an interesting idea. So now we have a function going one way. What about the other way? So if I now start off with a function from z cross x to y, can I get a function from z to y to the power x? So what does G do? G maps pair zx to an element of y. And now I need to decide how to map z to a function from x to y. And the function from x to y will need to map x to some value in y. What should that value be? Any ideas?
Should it map it to g of zx?
That's right. So we could just evaluate g at zx, right? There we go. Okay, that's interesting. So we have ways of going back and forth between these home sets. So I'm able to go that way, and I'm also able to reverse. And let's see whether these two are actually inverses of each other. And if they are, then we get the bijection we were looking for. Okay, so we will start with f, build the g, and then build the corresponding thing on the left side, and then see whether we actually get the f we started with or not. So to do that, I just have to replace my g of zx with the g that acts this way, right? And according to this, if g was defined this way, then g of zx would have been, let's see, what would it have been? It would have been f of z of x, right? Okay, so now let's compare this function right here with the function we started with. Both map z somewhere. Okay, that's good news. They both map z to a function from x to y. That's looking even better. Now we need to compare these functions, f of z and this mapping, right? Where does f of z map x to? It maps x to exactly f of z of x, doesn't it? So there we are. Going this way and then coming back, we arrive to the same function f. What about backwards? If I imagine I start with g, right? And then I create my f this way, and then I create my other g that way, do I get back the same g? Well, to see whether I get back the same g or not, I'm simply going to substitute in here f being this function, right? So what I've got here, f of z of x, what is that? That is taking z, applying f to it, getting this function, that's f of z, and then evaluating that function at x, and the value is indeed g of zx, right? So this is equal to g of zx. But then we get zx is mapped to g of zx, and that's exactly what g does. So the proof is done. Is everyone happy with this proof?
Yes, Prof.
Yes.
Fantastic. Okay, so we have a bijection, but as category theorists, we are still not happy yet. We just don't want just arbitrary random bijection. In category theory, we want things to be natural. and that's why we call those things natural transformations, because we want the kinds of transformations we're working with, we want them to be natural. And here I'm going to introduce a naive way of talking about natural transformations before I formalize them, which is a request from Soshan. In fact, this whole lecture today is dedicated to a combination of various requests from him. So thank you, Soshan, for that. So this bijection is natural in the variable z as well as the variable y. So not only there is a bijection between these homesteads, but moreover, this bijection is natural in these variables. What does that mean? What I just said. What does it mean for a bijection to be natural in a variable? Well, intuitively speaking, it means that if you swap this with z prime, if you swap the z with z prime, you would get another bijection which would be intimately linked with the bijection for z, in the sense that it will be defined the same way. But thanks to the notion of natural transformation, we can actually make this precise. But before making precise what it means for something like this to be natural in z or in y, first I need to get convinced that these constructions on each side, this one and that one, are functorial in those variables. I want to see that this is functorial in the variable z as well as the variable y. And I want to see the same thing on that side. And once I know they're functorial in those variables, then being natural in those variables will mean that we are dealing with a natural transformation between functors. So if this is a functor and that is a functor, then this bijection will be a natural transformation. So let's unpack these concepts. Hom z y to the power x is functorial in z. What does that mean? That means that by mapping z to, so now we are keeping y and x fixed, okay? We're only thinking of this as a function. So if we go back to calculus, which in some sense is the opposite to category theory, because in category theory we want to explain everything. In calculus we never explain anything, we just learn the rules. But if we, nevertheless, calculus is still part of mathematics, so there are still some links between the two. If we go back to calculus, we had this idea of a function of several variables there. For example, when we're differentiating functions, we might be differentiating in just one variable out of the several variables. And so this is kind of the process we're doing here. We have here a construction of several variables, the variables x, y, z. And now I want to fix some of the variables to see that as kind of constants and think of this as a function of one variable. and this case it's the variable z. So I'm seeing this thing as a construction that maps z to hom z y to the power x. This construction being functorial, or this being functorial in z, means that it should give rise to a functor, and the mapping of objects of which is described this way. But of course, we know hom is a functor. This is something we did already previous time. Let's just recall that. So it will be a functor from where to where, because of z being in the first component of the hom set. It will actually be a contravariant functor. In other words, it will be a functor from the opposite of my category. We are still working with the category of sets, so let's stick to that. From that category to the category of sets. Hom functors always take their values in the category of sets, right? So to create a functor now out of this construction, I have to describe what it does to morphisms. So if I have z prime, this will be mapped to hom z prime y to the power x, and a morphism in the in set op is of course a morphism, the same as a morphism from z prime to z in set, right? So this is in set, and that morphism is in set op. So let's call something that thing. So let's call this f. It has the same name in set f, according to how we define opposite categories. And so that f now should give rise to something on the other side in the same direction as the white arrow did, not the blue one. The direction of the white arrow was this. And now we want to create such a mapping based on the blue arrow, and this is something, as we said, we already know. So we will just take a morphism from z to y to the power x, let's say g, and we can compose that morphism with f to get a morphism from z prime to y to the power x, which is exactly something that will be an element of this, right? So the mapping on the right side is mapping g to the composite gf. And then the next step is to check that this is a functor. So we define it on morphisms, right? But now we still need to check it's a functor. It needs to preserve composition. But we already did that in the other lecture. That was the lecture on Janelidze embedding, I believe. That's the lecture where we checked that hom functor is actually a functor in both first and second variables. So you would want to go back to that if you haven't looked at that lecture yet. I'm just scrolling on my side at the notes of the lecture just to get convinced that we did that. But I think, yeah, I think we did that. Okay, so we get a functor out of the construction. And that's what we mean for something to be functorial, that it can be turned into a functor. But notice the ambiguity of this terminology. When we say that this thing is functorial in Z, why is this ambiguous? Could maybe somebody tell me? Why is it a bit ambiguous to say that this thing is functorial in Z? We seem to have a very well-defined functor, so what is ambiguous about it?
I'm just going to try. Is it because?
Yes, Sasha?
Is it because in the category, in this case in set, we don't know whether the morphism is running from Z to Z prime or Z prime to Z? I'm not sure. I'm just taking a guess.
That's one. Yeah, that's a good remark. That's one thing. We don't know what the domain of that functor is. Which category is the domain of that functor, right? That's one thing. Is it set op or is it set? We don't know that. The other thing we don't know is how the functor is defined on morphisms. We had to make up a definition on morphisms here. This construction only describes what to do with objects. It doesn't describe what to do with morphisms, right? Do you agree with that, Sarshan?
Yes, I agree.
Yeah. So it's a very bad terminology. It's really like, it feels like calculus now, where we we talk about differentials, but we never define what they are, and so many ambiguities in calculus like that, right? So ambiguities like these help us write less and think more. So once you agree that it was fairly obvious that this was really the best way we could have turned this into a functor, and anyone with enough experience of category theory would have done exactly the same as what we did, then we can skip the part of describing the functor, leaving it up to every other category theorist to recover that on their own in the fairly obvious way that we did it. Okay. And in a similar way, when things are skipped in calculus, they're considered to be obviously fillable. It might be technical work to fill the details, but the idea is that it can be filled in such a way that whatever imprecise things you're saying then become precise. But category theory does much better than calculus, because in calculus these things are not obvious at all. And in category theory, they really are. One might argue about this, of course. One might say that if you're a very experienced analyst, then it is still obvious for you. But I would challenge that. Bring me an experienced analyst, and I will convince that person that filling gaps in calculus requires so much development of formal mathematics that it might even reach the point where they lack knowledge in set theory, sufficient knowledge in set theory to formalize everything. Whereas here, filling these gaps is a very straightforward process for which we are well equipped.
Sorry, Prof, can I just ask a question then?
Yes, please.
I just wanted to hear from your side. How would you say that same idea, which you say is ambiguous, in a kind of better way, if that's the right way, such that the ambiguity is less?
Such that the ambiguity is less?
Yeah, it's reduced. Yeah, some kind of reduced.
Yeah, well, then you simply say this, that I can remove the ambiguity completely. I will say hom dash y to the power x, defined this way, is a functor from the dual of the category of sets to the category of sets.
Okay. Thanks. Yeah. Thank you. Yeah.
Mm-hmm.
Yeah.
And of course, for anyone who what category theories usually do, I mean, when we read each other's text where the other author has said something like this, what we do is we run in our head this definition and make sure it's everything is fine, and somehow the subject is such that two different category theories will be interpreting this functoriality exactly the same way. So there is some kind of rigidity in the subject, that because the whole idea, the whole point of the subject is to keep things simple. And that's also how it's applicable to mathematics, because when you formulate things categorically, then they become more apparent and more transparent and simple. So there is this kind of sense of simplicity that guides you in making precise statements that are made. But we don't have too much of such imprecise statements. I mean, it's only a few times that they arise. We did talk about this already in the first lecture, when I said that very often we will describe a category just by describing what its objects and maybe morphisms are, because composition will be obvious how to define it, even though there might be also other ways of defining composition. Yes, are there more questions?
Prof, I have a question.
Yes?
If we say that hom z y to the x is functorial in z, do we always mean that there exists a functor that maps z as an object in set op? to hom z y to the x in set?
Yes, we always mean that. However, if this is not home construction but some other abstract construction, you would have to be able to guess what the category is that is the domain of your functor. And as you rightly pointed out, maybe it was not so obvious that it should have been set up and not set. But if you try with set, then your f goes this way, right? And you've got a g going that way, and there's no way to get an arrow here, no obvious way at least. And so that's how you know that, okay, then we have to use the dual category. So it will always be, so the category will kind of be obvious because you took this object from the category. But then you would have to keep in mind that sometimes functoriality would mean dualizing, and sometimes it would mean not dualizing. Did I answer your question?
Yes, that's clear. Thanks.
Okay, so that's functorial in Z, and now let's look at functoriality in Z of the other construction, of this construction. So we have here hom Z cross X, Y. And using this slightly ambiguous terminology, I can even argue as follows. We already know that hom is functorial in the first variable. And taking Cartesian product with an object X is also functorial in that variable. We don't know that yet, but we could have established that separately. And then therefore this will be functorial because it will be composite of those functors. So let's spell this out. But I'm not going to break it down into a composite. I'm going to do it at once. So once again, because it's on the left side, this will be dual situation. So it will be functor from set up to set. Once again, X and Y are fixed when you talk about functoriality in Z. And this time, the construction maps Z to hom Z cross X, comma Y, and it maps Z prime. It will then map Z prime to hom Z prime cross X, Y. And it will map an F, which is in the dual category, and so it's actually F backwards in the original category of sets. It should map it to a function, and now let's see what is the obvious thing to do here. We often work this out by drawing a diagram, and usually category theorists draw this diagram in their mind, unless it's too big. I personally like to draw diagrams without even labeling the object. So in my mind, usually these things look like this. And I'm quite sure this is not just me like that, but many others are also like that. Okay, so we now need, like before, if we compare this with the previous picture, we just need to have something here to then compose them, right? So if this was a G, and we want to get an arrow here, I would just need to compose G with something there, and I have an F to use. And now how do I turn an F into an arrow from Z prime X to ZX? And the answer is to do F cross identity of X, which is a function defined by mapping Z prime X to F of Z prime, comma X. So you keep the second variable fixed in the Cartesian product. We haven't explored the notion of Cartesian product enough to have defined this for arbitrary morphisms between objects. Maybe it will be a good side thing to do it here, to just keep this as complete as possible. So if you've got product of two objects, and you've got another product, maybe with another object, X prime, and you've got an arrow here, let's call this F as before, let's call this arrow something else, maybe we want to call it H. You see, this is the horizontal parts are the product diagrams, I'm using the same pi1 and pi2. Again, another ambiguity, although these morphemes are different from each other. So pi1 label here just indicates to me that this is the first projection of the product, and pi2 respectively the second projection. And now what I have here is I can compose pi1 with f to get an arrow here. I can compose pi2 with h to get an arrow there, and then use the definition of product, according to which I will have a unique arrow here, which makes these triangles commute. And then that unique arrow is called f cross h. And in the category of sets, it will be defined by mapping a pair by applying each of the functions on the two sides of the product to the first variable and the second variable respectively. So the function here on the second variable, we are using the identity function, so that's why x just stays to be x. So then this composite G composed with f cross identity x will be how the value of the functor is defined. So it will map f to, it will map G to G composed with f, G composed with f times identity of x. And then we still want to prove that this is actually a functor. And as I said before, this functor will actually decompose into two functors, one going from set op to back to set op by this construction. So what is that construction? That is this construction of turning of, let me draw it here. So by that construction, Z maps to Z cross X, and Z prime maps to Z prime cross X, and the F that actually runs the opposite way maps to the arrow here, whose opposite is exactly the F cross identity. So this itself turns out to be a functor, which is not difficult to check by using the universal property of the product. And then that functor now is being composed with the other functor, which is something more familiar for us. This is hom dash dash y. So instead of checking that this thing is a functor, might be better to check that these two are functors, because one of them we already know, and then use the fact that composite of two functors is still a functor. So checking that this thing is a functor would amount to the following diagram. Imagine now I have another, so let's say checking composition is preserved, another product like this. And another f prime maybe here, and an h prime here. And with a similar effort, I will get the unique thing here, which is by definition is called f prime cross h prime. And now when I compose them, f prime cross h prime is being composed with f cross h. This composite here will indeed make another triangle commute, this one, where the violet arrows are simply composites of the green ones. So we can go this way, this way, this way, or which is the same as just going that way, which is still the same as going that way, and so on. And so these violet arrows will be corresponding arrows for the composites of the F's and the H's. So here we'll have F composed with F prime, and here we'll have H composed with H prime. And because that composite will make the triangles with the violet arrows commute, then that composite rightfully is, by definition, FF prime product with HH prime. And so that's how you prove that the construction of taking product is functorial. in fact, in both variables, in variable z and in variable x, but not for us. We're just interested when one of them is fixed. In other words, when this h is fixed to be identity x. And of course, if it's identity x, then composing identity x with itself will just give identity x. And so the fact that this preserves composition will then be an instance of this argument with h and h prime being identity x. And then also it's not difficult to check that this construction here will preserve identity morphisms as well. So the way this goes is that in the beginning, when you're learning category theory, you really kind of check everything by hand. We've been more or less doing that so far. This argument here, I think, was a bit quicker than the other arguments we gave before. It breaks things down a bit less. I kind of did it partially deliberately because, well, first of all, maybe I wouldn't have been able to arrive where I want to arrive if I had gone in more detail. But secondly, also, I want to show you that I mean, maybe some of you already can kind of guess that it works, even if we didn't go in too much detail. And if you are able to make such a guess, it means that you already have developed in yourself the ability to think categorically. But if you're not able to make the guesses, then it's an encouragement for you to check these things by yourself after the lecture and confirm that it really works. And that's an absolute must. So you must check such things a few times yourself, and then you develop this ability of kind of seeing these kinds of arguments in almost instantaneously without having to write everything out. And that skill is very important for learning more advanced things in category theory. Because if we really spell everything out every time, then it just becomes too long and too big, and it becomes too complex. So like with every other subject, I mean, we did say that we try to keep things simple in category theory, but certainly the subject does rely on our human ability to develop some skills that allows us to move on further to have things which initially would have been very complex to be able to comprehend them in a simple way. Okay, so what we've got here is an explanation of what it means for this to be functorial in Z. So we described the functor. And now let's establish that this bijection is natural in Z. So let's first of all describe what it means to be natural in Z, and then we establish the fact. So the bijection between these two things, let me copy this here. So this bijection being natural in Z means well, once we describe the functors, it will not be so difficult to describe what the naturality means. So we note first of all that the two functors we extracted from here are both of the same kind, in the sense that they both have the same domain and the same codomain. In both cases, the domain is set up and the codomain is set. So we could draw them as such in one diagram. So we've got set up, set, and we've got two functors here. One is the functor hom dash y to the power x, and the other is the functor hom dash cross x comma y. If I take these two functors, think of them as f and g. So let this be f and let this be g. Then what is f of z? Well, f of z is hom z y to the power x. What is g of z? Well, that is hom z cross x y. And what are we given here? We are given here a bijection between them, right? In other words, we're given a function that's a bijection. But wait a second, we are given such a function. Let's actually give a name to this thing. So let's call this function phi. But now phi, we are seeing this as y and x being fixed. But maybe we should still keep y and x as indices of phi. I will only keep z and y as indices actually, because I really want x to be fixed throughout the discussion. And then I'm going to call this phi zx and phi zy. And keeping the y fixed, this becomes a data of arrows, one for each z. So z is mapped by f there, it's mapped by g there, and for each z we have a function from fz to gz. This is exactly what amounts to natural transformation, except that a certain condition is to hold, right? So this phi becomes a natural transformation, and that's what it means for this thing to be natural in z. At this point, the compromise on rigor is far less than it was before. So functoriality still required us to describe exactly how these constructions are functors, but the naturality just requires specification of maps, which has been done already. We already know which phi we're talking about. So there is no choice here how to interpret this being natural in Z, except the choice of how to interpret these being functors. Okay, so let me remind you also the naturality diagram, the condition that defines natural transformation. So when I have a map phi from fz to gz for every z, for this to be a natural transformation, what we need to hold is the following. That if I have another z prime, and I have, so if I have a z prime, then I will have an amorphism between them, let's say amorphism, we call it small z, then this will give rise to a morphism between f of z and f of z prime, which will be f of small z. And in a similar way, it will give a morphism between g of z and g of z prime, which will be g of small z. And we will have another bijection here, which will be phi z prime y, right? So let's expand these fz prime and gz primes as well. So here we are, and there we go. Okay, so now we're saying that the natural transformation, the phi transformation is natural, and that by definition means, if you recall, that this diagram, the square commutes. So that's what we need to check. To check naturality of this bijection in Z, we need to first set up these constructions as functors of Z, and then check that for those functors, this square commutes. We will kind of check this by hand. So we will pick an element here, and then see where it goes there, and then see where it comes down here, and then chasing the same element on this side should give us the same element there, and let's see that that is true. So let's pick an element here. Let's pick element to be some function f from z to y to the power x. By phi, it will map to, remember what it maps to? It maps to a function that maps zx to f of z of x, right? So that's the function it maps to. And now we need to map this function according to gz. What does gz do? Remember what it does? So let's draw the diagram to recall what it does. We've got here z cross x. We've got here y. We've got here z prime cross x. And so I will take my arrow here, which is so remember, this is happening in the dual of the category of sets. So that means that the actual z is actually a function from z prime to x. And that thing there just composes these things with the function z cross identity of x. So that needs to be now composed with this function here. So this is the function that maps zx to f of z of x. And when we compose these two functions, okay, now I have a bad notation because I called this arrow z. Maybe I shouldn't have done that, but it's too late. Let me call element of z something else. Let's call this c. So cx gets mapped to f of c of x. I'm going to change this z as well to c. And now we need to compose these functions. We need to compose this function with that function, and it will be a function that maps c inside z prime. Let me call it c prime. C prime x is being mapped to where? I need to apply z and identity first, and then apply that, right? So I apply z and identity first. Then I get z of c, sorry, z of c prime, comma x, and then mapping it along this function, I get f of z of c prime of x. So let's remember that. So this is where this function got mapped to by the g of z morphism. So it must map to an element of the Hom set. In other words, a function from z cross x to y. And this function from z cross x to y maps c prime x to that value there, f of z of c prime of x. Okay, so maybe I was a bit too fast, or maybe I was a bit too unclear. If you haven't caught up with this argument, let's stop here for a bit, and maybe you want to ask a question, or maybe find a mistake if I made a mistake, or just give me an acknowledgement that I can go ahead and that you're happy with what we did so far.
Yeah, for me, I'm quite happy. I would need to work through the details on my own, but at a high level, it makes sense to me.
Okay, Sashan, so let's work the details together, if you don't mind.
Sure.
So let's go through this like step by step. So first of all, do you agree that an element of this Hom set is a function from z to y to the power x?
Yes.
Okay. Next is applying our bijection, and for that, let's scroll all the way up. This was our f, and when we applied the bijection, it worked like this. The pair zx maps to fz of x. Do you remember that?
Yes.
Fantastic. So now I go back here, and that's exactly what I've written. Do you agree?
Yes.
So
Yeah.
cx maps to f of c of x. You happy with that?
Yes.
Okay. Now I want to apply the g of z, and let's scroll up. So this is where we are. So you see, when I have a function from z cross x to y, right? By the functor, the way the functor acts on morphisms, this function maps to this composite. Are you happy with that?
Yes.
So let me remind you that we were describing here the functoriality of this construction in the variable z, yes?
Yes.
And to do that, we had to say what the functor does to every arrow, right? So we had an arrow in set op, which is the same as a function from z prime to z, function f, yeah?
Yes.
And this needs to give a function between the values of the functor. Do you agree with that?
Yes.
So now we're describing a function from here to there, which is constructed using f.
Yeah.
Okay, so we pick an element here, which is a g. You agree that this will be an element of this?
Yes.
Okay, and now I need to produce an element of this, in other words, a function running this way from z cross x to y. Do you agree with that?
Yep.
Okay, so now I'm just defining. I'm saying map g to the composite. So just compose g with that function here, and this is the function that applies f in the first variable and keeps the other variable the same.
Yes.
So if I write this element wise, what happens to z prime x eventually? Z prime x gets mapped to f prime zx, and then it gets mapped to g of that. G of f prime f of z prime x. So that's what this function does to z prime x. Do you agree with that?
Yes, agree.
Okay, now let's remember this. So z prime x gets mapped to g of f of z prime x, right? But the notation was switched around later on. So the notation we used later on had, instead of f, we had a z. Maybe that was not a good thing. So instead of f, we used z. So this variable f will become z. So maybe we actually copy this down. Let me copy this down and then compare with the notation there. So there we go. So this is what happens to. So if I begin with a g that's from z cross x to y, yeah, and then I move here, it will be mapping z prime x to g of f prime z comma x. You happy with that?
Yeah. Yes.
Okay, so now what is my z prime? My z prime x. My z prime x is called c prime x because I changed. It's my fault because I changed notation. So my z prime x is c prime x. Now I need to map that to g of f of c prime x, right?
Yes.
Okay, so let's remember that. So this needs to be g of f of c prime x. But what is g? G is the function I had here, right?
Yes.
What does this function do? G of cx is by definition f of
CS.
c of x, isn't it?
Yes.
And now I run into a problem, don't I? Okay, another notation difference is that the f and the z. So we're looking here at g of z. So previously the morphism we were mapping was called f, yeah?
Yes. Yes.
Now it's called z. So I need to change this with z. So you happy with that?
Yes. I agree.
Okay, so now we want to apply g to this pair, but how does g apply? G evaluates f in the first component and then evaluates that with x. So you see f of the first component and that evaluated at x.
Yes.
Does that make sense?
Yes, that's clear to me. Yeah.
Okay, so yeah, I'm not sure. Maybe it was still not very clear. I mean, I think the confusion could have been caused because we need to remember these notations in order to follow the argument. But because I changed notation, it could have brought in confusion. Did you want to say something, Soshan?
No, sorry, that was my son. For me, for me, it's quite clear because I was able to follow each individual step. And so I think if I had to rearrange it with the consistent notation, I don't think I would have any challenge. So yeah, this was really helpful and clarifying for me.
Great, thank you very much. Thank you. Okay, fantastic.
Sorry, Prof.
Yes.
Can I ask the definitions for the functors f and g? Where do they come from?
This is what we defined here. What is the f functor? F functor is our home z y to the power x functor, and g is this functor. You see, f is this functor and g is the other one. And they were defined right here. When we said that this is functorial in z, we defined how this thing is a functor.
Okay.
And the same for the other one.
Okay, thank you.
Now we need to still chase. Yes?
Sorry, Prof, just a second. Can you just roll up a bit? Just a bit up. Up again. I want to go to where you've got, yeah, there, yeah, stop there. You see this F, the blue F from Z prime to Z.
Yeah.
On one direction, you named it as F from Z to Z prime. I was just wondering, wouldn't it be more convenient or self-explaining if we then the blue F, we could just name it as F up?
No, because it depends on how we define the dual category, but the usual definition says that the objects and the morphisms are the same as before. Okay. It's the orientation that has changed. So
keep the same name. Yeah.
Yeah.
Okay.
So the new domain map is the old codomain map, and the new codomain map is the old domain map, but the arrows themselves are identical to the arrows we had before in the original category.
Okay. All right. Thanks.
But I agree. I mean, in terms of explaining, it's maybe more convenient to have different notation, but they actually are the same object.
Sorry, Prof.
Yes.
From the universal property here, the way you were dropping this pi, I didn't get well. The pi, they are different, but you are just assuming that they are the same. I didn't get well.
I didn't assume they're the same. I just simplified notation. So if I didn't simplify notation, I should have drawn it like this. I should have added subscripts or something like that. Maybe I'll add subscripts maybe after.
Okay.
Maybe the top, but it doesn't mean exponential. Okay. So
okay.
z comma x, z comma x, because this is projections for z and x, and the other one is projection for z prime and x. So it should have been z prime, x prime, and so on.
Okay. Thank
but
you.
I just dropped them because it becomes too excessive notation.
Okay.
Prof, can I just check something about the phi? We had a map between, we had a function originally. Yeah, but in the, we're saying phi is the natural transformation that comes from these components that we defined, the phi yz, I think it was, or the phi zy. So are we saying, am I right in saying that the different components of the phi are the phi zy and the phi z prime y?
Yes.
Okay, so but the way you wrote, so the way you wrote it right now, it should have still been phi, right? Not the phi zy as the natural transformation.
So the family of phi zy's, the family of phi zy's, where we keep the y fixed, this family of maps can be called phi y because we still have y fixed.
Oh, I see. I see. Okay. Yes.
Mm-hmm. Great. Thank you very much for the questions. So let's
sorry, Prof. On the same phi y, since we have that the y and the x are fixed, but we are just varying the z. Would it be true if I just write the natural transformation as the family phi z, only phi z?
Yes, yes,
Okay.
but because later on in the same lecture, I want to also make y change. That's why I'm still keeping y, but I will never change x, so that's why I'm not using x.
Okay, thank you.
Prof, sorry, another question just came to me.
Yes.
Does this mean to say that a bijection is natural in Z, we would, by definition, first have to require that the two objects on either side of that bijection,
Constructions.
yeah, the two constructions are functorial in Z. Okay.
Exactly. And to sort that out, you have to specify what these functors are.
Right. Got it. Thanks.
Okay, so let's go back to checking that this thing is indeed a natural transformation. Now we want to chase the same element along the other path in the square. So if I now map f there by fz, remember that was just precomposing with the z, so that f will map to f composed with z. And then you see it maps exactly here, right? That's what we did with things, right? We turned it into a function of two variables by evaluating it one variable first and then the other. So I'm not going in detail there, but I think it's fairly obvious that it works. Okay, so we now have kind of spelled out what it means for this thing to be natural in Z, and we have proved that it is actually natural in Z. And we would want to do something similar for the other variable, which is the variable y. So, but I'm actually not going to, because of keeping in mind what we want to achieve in today's lecture, I'm not going to go detail in the other case. And in a sense, I mean, these details will be fairly routine work to figure them out. One just needs to get the insight of how these things work, and then anyone can work them out. So we can similarly show that this bijection is natural in the other variable. So we can have a bit more precise notation to this now. So we called it phi of what was it? Y zy, right? Phi of zy, which is a function from there to there. Similarly, it can be shown that this thing is natural in Y. And remember, this means that first of all, we will have to first build, kind of reconstruct these as functors, this time with Z being fixed and Y being the varying object. And then prove a naturality square for them. And so the point we arrive to now is the definition of exponents in an arbitrary category. So we've now shown that these naturality properties hold in the specific category of sets. But now we can use that property to define what an exponent is in a category. Definition. Exponentiation specifically raising to power x often, sorry, in a category C. We do need this category to have binary products because we are using binary products to define exponentiation. Exponentiation in a category C with binary products is a functor from C to C. So we can call this functor like this maybe. Such that there is a function phi zy from hom z y to the power x to hom z cross x y having the following two properties. Firstly, I apologize. I now realize that I actually wanted to present my bijection mainly as the function going backwards. It will be nicer like that. So let me allow to make that slight modification. So this function will then be kind of inverse to the other one we've been considering. We know it's a bijection, so that should be fine. And then, but I wouldn't allow myself to call this phi anymore. So let me call it something else. Let me call it. I don't want to call it phi inverse because I want that to use that as the starting thing. So let me just call it maybe psi instead of phi. So our psi is now the inverse of the phi we had before. So it's a function. There is a function psi having the following two properties. So first of all, that psi is a bijection. And secondly, that psi is natural in both z and y. Now you might tell me that's not fair, the modification we did, because we only showed naturality of its inverse of phi. How do we know psi is also natural, right? It turns out that when you have a bijection between two functors, which is natural, then inverses will also give a natural transformation. It's not a difficult thing to check. But let's not go into those details now, because I want to show you the bigger picture of what's coming out from all of this. The fascinating thing that coming out from here is that this natural bijection turns out to be simply an equivalent way of defining an adjunction. We have two functors here. One is the functor dash cross x. The other is the functor dash to the power x. For any two functors in the place of these two, let's call this thing f and let's call that thing g. To say that there is a bijection between fxy from fxy to hom x gy that is natural in x and y. Sorry, now I very ugly, in a very ugly way changed my notation. I apologize for that. I need to use z, not x there. So to say that there is a bijection that is natural in z and y is nothing other than to say that f and g form an adjunction, which is a kind of very powerful fact. So we're led back to this idea of adjunction, and now we actually can see exponentiation. You see, exponentiation will be the right adjoint. I usually use g for right adjoint. We can see exponentiation as the right adjoint of the other functor, which is the multiplication by x. Okay, if there is an adjunction, there must be unit and co-unit of adjunction, right? So let's actually describe what these are in the case of the category of sets. So we've got an adjunction here. Okay, so the unit of adjunction should do what? It will be a natural transformation from x to g f of x. The co-unit of adjunction will be a natural transformation from fg. Okay, I'm still using x. I need to use z instead to match with the notation we've been using there. The co-unit of adjunction should be a natural transformation from fg to g, to the identity functor, right? So to the arrow to y. So that. So let's find these maps in our case. What are they? So do we have a canonical map from z to what is gf of z? F of z is multiplying z by x, right? So z cross x, that's f of z, you see here. And now we need to raise that to the power x.
Sorry, Prof.
Yes?
The unit is unit in z, ne? And
yes, thank you. For the other one, we will have to take g of y, which is raising y to the power x, and then applying f to that, which is multiplying that by x. So from there, we need to go to back to y. So do we have such maps? Well, in fact, we do. Where can we map z? We can map z. We have to map it to a function that maps x to where? So what do you think I should put here? It should be an ordered pair inside z cross x. Do we have a natural function mapping x somewhere that's based on z? Let me repeat the question. So I mean, having remarked that, in fact, this is just another way. I mean, the definition we gave here for exponents is just another way of defining an adjunction. We now are anxious to find what will our adjunction data be for exponentiation and Cartesian product, where Cartesian product is seen as a functor with one variable fixed. So at least we want to build these maps. Maybe we will not show that it's an adjunction. Maybe we can leave it as an exercise, but at least let's try to see what these maps look like. And so I will need to map I will need a function from Z to there. And do I have such a function? So I will have to map an element of Z to a function from X to Z cross X. So then X will have to map where?
To maybe the ordered pair ZX.
That's right. Yeah, that's a very natural map we have there, don't we? And I think it's clear that this map will be natural in Z because of naturality of how it's defined. So in general, whenever you have a construction that's defined in a kind of intuitively natural way, it ends up being a natural transformation. And on the other side, if we have a function f and a variable x, we now need to map it to an element of y. Any ideas how to do that? So f will be an element of y to the power x, so it's a function of x to y. And then we have an element x of x. Where can we map this pair?
To f of x.
That's right, yes. So this co-unit of a junction will be the famous evaluation function that evaluates a function at a variable. Fantastic. We can check the triangular identities for a junction to get convinced this is actually an adjunction. And let me skip over that because, again, you just look back at the definition of a junction. You might not remember it by heart, but you can look back at our notes, see exactly what needs to be satisfied for this to be an adjunction, and you can by hand yourself very, very easily check that indeed these two maps, which are natural in Z and Y, which you can still check as well, these two maps will actually give an adjunction. And of course, after that, the next step would be to obtain this general result that any adjunction always gives rise to such a natural bijection, and the other way around. If we have a natural bijection like this, we get an adjunction out of it. So instead of going through all these technicalities for today, let us explore what other examples of exponentiation can we find in other categories. After all, if we don't have any other examples, if it's just something specific to sets, then why bother doing all of category theory around it? And remember how we motivated the notion of a category based on two different ideas of a monoid and of a poset. So now let's go back to posets. What is exponentiation in the realm of posets? In the realm of posets, so this will be an example. Exponentiation in posets. Well, first of all, when our category C is a poset, so a partially ordered set, right? Seen as a category where arrow means that you've got one element less than the other. So having an arrow from X to Y means that X is less or equal to Y. And maybe I want to use small x and y for that. So that does mean that Hom set of x and y has cardinality always less or equal to 1, right? Because there either is an arrow or there isn't. That's how we view a poset as a category. So Hom xy equals empty set when x is not less or equal to y, and Hom xy equals some one element set, maybe bijective to a one element set, when x is less or equal to y. Okay, having that in sight, let's explore what is exponentiation. We could do it in two different ways. One is using the adjunction, the unit and the co-unit construction, and the other is using the definition we explored today, which is this natural bijection. And let's do the second way, because that's what we spend most time on today. So let's now write this bijection out in the case of posets and examine what its naturality means. So we're now saying that Hom, and let's do it in the same direction we were we were building phi so that we stick to the to kind of so that it's easier to compare to what we did earlier. So we're going to establish a bijection from we're going to see that we have a bijection from z to this mysterious object y to the power x. Bijection, we're looking for a bijection between this and from z cross x, y. But what is cross in a poset? What is Cartesian product in a poset? So recall the definition of Cartesian product. So if I've got two objects z and x, their Cartesian product needs to be less than both because we've got these arrows. But now, since there's only at most one arrow, we can get rid of the labels for arrows. So this just means that z cross x will be less or equal to z as well as less or equal to x. The mere existence of these arrows guarantees that, and that's actually equivalent to that, right? And then we have the other condition that if I have C with two other arrows, right? So if I have C less or equal to z cross x, then there must exist unique arrow, making triangles commutative. Well, when an arrow exists, of course, it will be unique because in a poset, we always have at most one arrow between two objects. So the uniqueness part can be dropped off. And also the commutativity of the triangles is clear because in a poset, there is always at most one arrow. So the composite will definitely match with that. So the definition of a product just reduces to the statement that for any C that's less or equal to Z and X, sorry, I didn't write it correctly. Yeah, any C that's less or equal to both Z and X, any such C is also less or equal to Z cross X. What is this a definition of? So you've got this mysterious element of the poset, the Z cross X element, that has the property that it's less than both Z and X, and if anything else is less than both, then that thing is less than that as well. What is that element? Is it something familiar?
It's the meets of Z and X.
That's right. That's exactly the infimum of the two elements at Zx, in other words, the meet of Z and X in the poset. So that's the usual notation one uses for that, right? If this is the poset of logical statements, or rather the pre-order of logical statements, then the meet will be the conjunction, the logical conjunction. Huh? So in that model, less or equal means that you've got that one statement implies the other. Okay, so the product becomes the meet. So let's replace that. And now we're saying that this first of all, we're saying there should be bijection between these two things. So that we're still trying to figure out what this thing is. We're saying that there should be bijection, and then that bijection on top of it should also be natural, right? But now if you think about it, the naturality would be what? Let's go back here. Naturality is commutativity of a square like this, right? But our home sets, in the case of poset, these things are always either empty or singletons, right? So if you think hard enough about it, this square, which needs to commute, when these home sets are always either empty or singletons, I mean, the most you can have in each of these sets will be one element. And of course, then such a diagram will always commute, right? Because commuting of the diagram means that you pick an element here, you go there, you go here, and that must end up being the same as chasing the element this way. But if this set has at most one element, then it will end up being the same, right? So the requirement of naturality drops completely. If I have a bijection, it will be natural because of the fact that the things I've got here have at most one element. Just like here, the uniqueness of this thing dropped because of the fact that we're working in a poset. So we now just want to say that there is a bijection between these things. But let's think further. What does it mean that there is a bijection between these two sets? These two sets are either empty or singletons, right? If we say they're bijective, it means that one is empty if and only if the other is empty. Or in other words, one is a singleton if and only if the other is a singleton, right? Because if that's not the case, if one of them is singleton and the other is empty, then they can't be bijective to each other, right? And in fact, it's equivalent, it's a characterization. So the existence of a bijection is simply says that this is non-empty if and only if that is non-empty. But what does this mean that this is non-empty? It means that z is less or equal to y to the power x. What does it mean that the other one is non-empty? It means that z meet x is less or equal to y. So now we're saying these two are equivalent to each other. And let's put them once again in the reversed order, which is something I should have done from the start. I apologize that I kept this the other way around. I want to put it in the reverse order so that it reminds you of something. For those of you who know what Galois connections are, this is reminding you of a Galois connection between meeting with x and exponentiating with x. And that's not surprising because Galois connections are just adjunctions reduced to posets. Does any one of you know exactly in a poset what is this thing called? Which is such an element y to the power x so that it fulfills this equivalence for arbitrary z, x, and y? So
It's got something to do with the hating operation.
exactly, yes. This is the implication of the hating algebra. In fact, a hating algebra is simply a poset that has products, finite coproducts or sums, and the exponentials. So for the rest of you who might not have seen this before, let me take a specific example of a poset where the elements of the poset, it will actually be rather a preorder, where the elements of the preorder are mathematical statements. And less or equal means that one statement can be used to prove another one. And now this equivalence says that this statement is such a statement created out of statements x and y that to be able to prove that, or rather to be able to deduce this from z, it's sufficient to deduce y from z and x. So imagine you've got a proof in which you assume that z and x are both true. So assume that z and x are true. And in this proof, with this assumption, you've been able to conclude that y is true. So assume that is true, and then you say, okay, from that assumption, we conclude y is true. Having such a proof would be equivalent to having a proof where we start with z as our assumption, and trying to conclude whatever that thing is, that will be our exponential. But I mean, if you go back to your basic understanding of mathematical proofs, what will we be able to prove in terms of z once we've already proved that z and x gives us y? So the thing here must be in terms of x and y, and we must be able to prove that based on the assumption z if we already know how to prove y based on the assumption z and x. What is this thing here?
Would it be something like
Oh, sorry.
Yes, Soshan?
I was going to guess something like if X is true, then Y is true.
Fantastic. That's implication. X implies Y. And I'm sorry, Gregor, I didn't let you speak because we know this from the logic course, but you might we didn't know the link with exponential. But is that what you're going to say?
Yes.
Yes.
I thought nobody else would say it, but yeah.
Yeah. So well done, Soshan. Indeed. And these two proofs would be equivalent because, I mean, first of all, if I have such a proof, then clearly I can produce this proof, right? I'm going to assume Z. To prove X implies Y, I will have to assume X as well. And then I will apply the proof I've got here, because now once I assumed both Z and X, I can make use of the fact that Z and X is true, and then get to Y the way I got it here. But also the other way around, if I have a proof of this kind, where I assume Z and I prove that X implies Y, I can build a proof of this kind. How? I assume Z and X are true, right? But that in particular implies that both Z and X individually are true. But since I already have a proof from Z going to X implies Y, I will be able to write X implies Y here, because I already know that from Z I can get there based on this proof. And then I do what? From these two, I can get to that by which rule? What is the rule called that allows me to get from the fact that X is true and X implies Y is true to the fact that Y is true?
Modus ponens.
That's right. Modus ponens is there. And in fact, modus ponens arises as, I mean, it arises from the adjunction definition here by substituting suitable values there, which we kind of witnessed here. So that's what we get here. Exponentiation in poset becomes implication. And it is quite fascinating because in sets, exponentiation was a set of functions. And here it's implication against something that has to do with arrows, right? But it's a bit different. But still, there's some kind of notational similarity even. Huh? And this is an example of the kind of insights that category theory brings. You see, because before looking at things from using the lenses of categories, we would never imagine that something as fundamental as exponentiation of sets and something as fundamental as implication of statements in logic, that they have to do anything with each other. But now it turns out that they're very intimately related with each other, and that relation comes from the fact that Cartesian product of sets is intimately related with the meet operation. And that relation comes from the fact that both of them are instances of a product of two objects in the category. And then exponentiation and implication, both of them arise as, so with one variable fixed, right? They arise as right adjoints of taking Cartesian product or meet with one of the variables fixed there. And there is a general effect that if you've got right adjoint of something, they will be always isomorphic to each other. So this actually does define the thing up to isomorphism. So if you have two different exponentiation functors here, if we had two different exponentiation functors satisfying this bijective requirement, they will actually be isomorphic to each other by applying the general theory of adjunctions.
So, Prof,
yes.
yeah, there's a term there which is I didn't say who said it. Is multi something? I didn't get the term very well. Multi exponents or multi something?
Modus ponens.
Can you please let us?
Modus ponendu ponens is a Latin term. Oops, I'm not sure. I think it goes like this. It's a Latin term that is the name of this rule, where from the fact that X is true and the fact that X implies Y is true, you can conclude that Y is true. The literal translation, according to Wikipedia, at least from Latin language, is that the method of putting by placing. I don't know if it's very suggestive, but that's, yeah.
Oh, okay, thanks.
Okay, so let's just summarize what we did, and then we'll end there. So we started off with exponentiation of numbers. Then we saw that exponentiation of numbers actually has something deeper behind them. That's exponentiation of sets. And then we tried to look at exponentiation of sets from the lenses of looking at sets as objects in a category. And we immediately wrote this one down, this bijection, but we were not happy with the fact that we're using the terminal object here, because in other categories, coming out from the terminal object will not be a very useful thing. In many cases, it will just be trivial, one element set, this one. And so we swapped from considering actual elements to considering generalized elements. That's when we allow the arrow to have arbitrary domain rather than a singleton. That links up with the lecture on Yoneda embedding, where we describe the intuition behind generalized elements. And then by switching to generalized elements, we obtained some kind of bijection, but we were still not happy with that. We wanted this bijection to be natural. And once we required that this bijection is natural, we saw that actually it is natural. So we can describe exponentiation that way for sets. But then we could use the same definition in a general category. And then it turns out that it actually defines an exponential functor as an adjoint, as a right adjoint of the functor of taking product with a given object. And once we had this general notion of exponentiation in a general category, we then applied it to a very specific category, the preorder of mathematical statements, where we saw that the exponential object, so something raised to the power another thing, a statement raised to the power another statement, is simply implication of statements. There are many consequences of these notions and facts. Like for example, we said earlier that in the lecture on adjunctions, we mentioned that right adjoint, for instance, will always preserve finite limits. So it will always preserve finite products. We can apply that fact here. We know that products are meets here, so we now know for free that if I take y1 meet y2 and raise that to the power x, in other words, imply that from x, that will be the same. So if and only if as implying from x individually and then taking the meet. And of course, this is something familiar to us in logic, because if I want to prove that x implies conjunction of two things, it's equivalent to proving that x implies each one of them. And this way you can get various rules of logic out of just general properties of adjunctions, or you might want to get various rules of exponentiation out of properties of adjunction. So the fact that exponentiation preserves products for per-sets gives us this, for statements, for the preorder of statements gives us this, but for sets it gives us that y1 cross y2 to the power x is bijective to y1 cross to the power x cross y2 to the power x. And this is a familiar exponentiation rule, right? A times b to the power c is the same as a to the power c times b to the power c. And so not only does this approach of looking at things from the lenses of categories, not only are we able to bring out concepts that kind of unify different fundamental concepts into one concept, but it also has practical use, because now we can apply the general facts we know about these general categorical concepts in the concrete situations to derive some of the consequences which might or might not be familiar for us in those concrete situations. So that was the kind of the goal of today's lecture, to show you how what the purpose of category theory is, in a sense. And we did that on the example of exponentiation. There's a suggestion from Soshan, and also the other thing we touched on was this common way of talking about things being functorial in a variable or being natural in a variable, which was another thing that Soshan requested for us to explain what it means, and we managed to do that because it was exactly the topic where such terminology does arise. Do you perhaps have any other questions? Soshan, have we addressed your requests?
Yes, absolutely. It was beautiful. Thank you.
Sorry, I don't think I heard you. Did you say something?
I was saying yes, absolutely. My requests were addressed, and it was really beautiful explanations. Thank you.
Great. Thank you so much.